You've gotten that bug report, right? A user just says, the site is slow. Well, today, we're going to go on a little detective mission to solve that frustratingly vague complaint, and we're going to trace it all the way down to the single line of code that's causing all the trouble.
Oh yeah, we've all been there. That vague complaint comes in, and the hunt begins. You're just scrambling through these endless, totally disconnected log files, trying to find a needle in a digital haystack. It's all reactive, it's slow, and let's be honest, it's frustrating for you and your user.
And in this case, the user is absolutely right. A really key transaction is taking 4 agonizing seconds to complete. Now here's the problem. Our logs, they just tell us the request started and, well, it eventually finished. They don't tell us why it took so darn long. And that's exactly where our investigation begins.
Okay, let's dive in. Our first stop is the Sentry performance dashboard. I want you to think of this as a high-level map of our crime scene. It's where we can see all the activity and start looking for clues. So the dashboard immediately gives us a list of all our application's transactions. And whoa, that get/API/checkout endpoint, it sticks out like a sore thumb. Just look at that P95 latency, 4,000 milliseconds. Yep, that's our 4-second transaction, right there.
Now what's really interesting here is why we're so focused on P95 latency instead of, say, the average. See, average latency can actually hide the pain. It kind of smooths out all the outliers. But P95 latency, that shows us the real-world experience of the slowest 5% of your users. You know, the ones who are most likely to get fed up and just leave.
Sentry also gives us this handy thing called an abdex score. It's basically a quick way to measure user satisfaction based on response time. A score near 1.0 means everybody's happy, but a score like 0.72 for our checkout endpoint, well, that tells us a pretty significant number of users are having, at best, a tolerable experience, and at worst, a really frustrating one. So now that we've found our slow transaction, it's time to dig deeper.
Okay, so we know which transaction is slow, but we still don't know why. So let's go ahead and click into that slow checkout transaction and follow the trail of evidence.
Now to understand what we're about to see, we got to know 3 key terms. First, a trace. That's the entire end-to-end journey of a request. It contains transactions, which are calls to a single service. And then each transaction is made up of spans, and those are the individual operations like a single database query.
And this diagram just illustrates that parent-child relationship perfectly. A trace is the whole story of the request, you know? Transactions are the chapters, what happened in the front end, what happened in the back end, and then the spans. Those are the individual sentences, every single database query, every API call, every function execution.
And this is what you get, the trace waterfall. It's this beautiful, chronological breakdown that shows us exactly where time is being spent in that 4-second request. You can see each bar is a span, and its length tells you precisely how long it took.
And there it is, our smoking gun. We can see right away that one database operation is taking up 3.2 of the total 4 seconds. Just like that, we've gone from a vague user complaint to a specific, super slow database query in just a few clicks. But wait, it's not just one slow query. As we look closer at this waterfall, we start to see a very suspicious, repeating pattern of nearly identical database calls happening one right after another. This is a classic performance anti-pattern.
So, what on earth could be causing dozens, maybe even hundreds, of sequential database queries for what should be a single user action? Well, this is the signature of a very common and very costly problem.
This, my friends, is the classic N+1 query problem. It happens when your code makes one query to get a list of things, and then, inside a loop, it makes a separate query for each and every one of those things. It's an absolute performance killer that often happens silently, especially when you're using an object relational mapper or an ORM.
And here's the crucial part. It can be so easy to fix. I mean, look at this Django example. The before code makes 11 separate queries to the database. The after code adds just one method, select_related. All that does is tell the ORM to eagerly load the author data in a single efficient query. One line of code takes us from 11 queries down to just 1. That's huge. All right, let's put this all together and see how it works in a real-world scenario. From the moment a user feels that pain to the moment you can deploy a fix with total confidence. So imagine this. A user reports a slow checkout on their phone. At the exact same time, a Sentry alert automatically fires because your P95 latency just crossed the 2-second threshold you set. Your engineer opens the alert, sees the trace, and bam, immediately identifies an N+1 query that's executing 47 times. They can then link that trace directly to a new ticket, complete with all the context, and now the team knows exactly what needs to be fixed.
This whole workflow just transforms performance debugging from stressful guesswork into a fast, repeatable 5-step process. You get an alert, you identify the problem transaction, you analyze the trace to find the bottleneck, you pinpoint the root cause, and finally, you resolve it with a fix. You're going from alert to resolution in minutes, not hours or days of digging through logs.
And that leaves us with a final thought to chew on. If a tool like Sentry can help you find and resolve an issue like this in just a few minutes, what other performance bottlenecks are currently hiding out in your code, silently frustrating your users just waiting to be discovered?